Okay. So we have connection, and now we can start. Hello, everyone. I'm Maura Pintor, and I'm an assistant professor at the University of Cagliari. Welcome to a new event of our seminar series on machine learning security. Before we start, I would like to share a few pieces of information before the event. So first, the event is live streamed and recorded, and you will find all the recording also in our website and YouTube channel, so feel free to check it out. If you also want to know more about machine learning security, in our YouTube channel, we also have a course that is free and available for everyone. And now I want to thank all the co-organizers of this event. And now I leave the stage to Raffaele, who will introduce the speaker for today.
Thanks, Maura. Hello, everyone, again. I'm happy to introduce today's speaker, Sahar Abdelnabi. She's an AI security researcher at Microsoft Security Response Center in Cambridge. Previously, she was a PhD candidate at CISPA Helmholtz Center for Information Security, advised by Prof. Mario Fritz, and she obtained her Master of Science degree at Saarland University. Her research interests lie in the intersection of machine learning with security, safety, and sociopolitical aspects. And this includes areas like understanding and mitigating failure modes of machine learning models, their biases, and their misuse scenarios. Then how machine learning models could amplify real counter-resisting societal and safety problems, and emergent challenges posed by new foundation and large language models. Okay, Sarah, the stage is yours.
Okay, hi. So thanks everyone for thanks Maura, thanks Rafael for the introduction, and thanks so much for the invitation. So I hope my voice is clear now, and yeah, that's the case. I will start sharing my screen, and hopefully this time it will go smoothly without problems. Okay, so can you see the screen?
Yes, that's good.
Yeah. Okay, great. Hopefully you'll see also it moving, right? So I will try to keep an eye on the chat, but in case I missed something over the chat, please interrupt me if you have any questions, and of course also welcome any questions during the talk or at the end. Okay, so today I would like to talk about some challenges in evaluating large language models and some new security and safety risks that are posed by current LLMs. So before I start, I would like to give some brief overview of things that probably all of us know, but I would like to give some brief, very, very, very brief history of how LLMs are being trained and how they are deployed in current ecosystem. So in very basic principle, LLM are trained as unsupervised way to predict the next token on very, very large amount of text over the internet. But then, as we know, they are later used in many plugins, in many copilots, in many applications as interactive models or interactive chatbots that deal with interactive real-world tasks. So the jump from this to this is not very clear. So most of the training are done in unsupervised way, but we have later stages of supervised fine-tuning or RLHF, but these training strategies are introduced at later stages. So the question here that I would like to talk about today is that are these new applications and adoptions of LLMs, are they compatible with what we had as static single-turn NLP datasets? And by static single turn, I imagine a scenario where like we have a task summarization data set or like a QA benchmark. Usually it's non-interactive, it's not multi-turn, and the answer is quite short. But many of the applications that I talked about before, they require prolonged multi-turn interaction with users. And in general, having these dynamic multi-turn setup of LLMs and chatbots, they come with some new challenges. So, for example, in this recent work here, we can see that if you have a longer multi-turn interaction with an LLM, so you start asking the LLM about task one, but then during the conversation, during the chat, you switch to another task, and you can see a degradation in performance compared to if you start the conversation from task two without the previous task switch. And this is, of course, not really convenient because we don't want every time to chat with a chatbot to restart the conversation every time, especially if you really want the output of the, or you need to build over the conversation that happened already in the history. And also, we may remember earlier when chatbots were deployed as search engines, is that when they had some longer conversations with users, they started to getting more far away from the aligned behavior that they want them to have, and they start to have like some undesired behavior, like being hostile towards the user. And we also see that in recent work, we can see that longer multi-turn interaction, they can have more safety implications. They can enable more kinds of jailbreaks. So in this example here in this recent paper, is that instead of asking the LLM directly about how to make a bomb, it starts from a conversation about history and how to make bombs, but without actually referring the word bomb. So in general, you need to, it's hard to filter out each of these questions individually because each of them might sound benign. But if you take the whole conversation history, you can find that it's not a safe behavior. And in general, if we use LLMs as assistants or as co-pilots, a lot of tasks, even the simplest one like scheduling an appointment, they require some sort of complex multi-turn communication and planning skills. So in this example here, if a user asks an LLM or an agent to schedule an appointment and the user specifies that it's urgent, the LLM should translate that to the earliest possible appointments and should be able to negotiate better times and also should be able to rank the different options in order to find an option that sort of satisfy the word urgent or the requirements of the user. And also, the one current failure of some of the evaluation benchmarks that we have at the moment is that this recent work, this very recent report that was released a couple of days ago, is that we found that models really tend to overfit the evaluation benchmarks that we have. So we ask the question here, is it possible to have an evolving benchmark or a dynamic benchmark where it evolves with models and also easy to adjust and adapt in order to test future models that might be more capable and also to rule out memorization or overfitting aspects. The last bit of motivation that I would like to talk about before moving into more details about the work that I would like to talk about today is that I would like to usually I think of LLMs and also a lot of aspects of ML security and attacks from the perspective of having static setup to dynamic setups. So static here, I mean that you have a single turn model, like a language model that's non-interactive, or you have a static image classifier or NLP classifier that was trained once. And in here, in order to attack this classifier, you optimize your attack image, for example, once, and then this is distributed for all models that are not changing in context when you distribute this attack from one model to the other. But in contrast, I think now with multi-turn interactive models, we have more dynamic setup where the output of models may vary greatly according to the conversation history or according to the input to the model, to the retrieved input in case of search engines. And also, if you have attacks such as prompt injections attack, where an attacker may inject a prompt somewhere in the retrieved input, this could the attacker would do this once, but the output of the attack itself may differ from one conversation session to the other. And oh, sorry, this is a leftover from previous slides. So extending over to multi-agent setup, because I imagine that in the future we might end up with like multi-agent setup where, for example, we have different LLMs representing different entities, and it could be possible that one of these agents or one of these LLMs could launch attacks or could attack the other agents. And given all this introduction, so now this is a very long introduction to say that we have a problem with evaluation benchmarks and with evaluation setups that we currently use to evaluate LLMs. And in this work, I would like, and in this talk, I would like to talk about a recent work that we did, and I think it tries to address some of these limitations of evaluation benchmark that I talked about before. So what we do here is that we propose to evaluate LLMs with interactive negotiation games. And it's interactive. It means that the models are engaging in a conversation over a prolonged chat history, and it's also multi-agent. So it seems that it means that we have more than one LLM or one entity. So a motivation of why we use scoreable negotiation. So by scoreable here, I mean that each agent has goals and it also has a set of scores, and it tries to optimize over these scores in order to reach better deals according to the set of score it has. So the first reason of why we use this is that this entails many important skills that it's important to measure in agents and in LLMs. So because the agent should keep track of its scores, it should be able to calculate the value of these scores. So this measures arithmetic calculations that are important to measure. And also, in order to reach agreement with other agents, it should be able to make inferences about the value of these deals to others or how others would prefer the deal to be. And this is usually something that's not straightforward to infer because the scores are secret to each agent. So the agent has to rely on the negotiation history, the negotiation interaction, and also common sense reasoning in order to make inferences, correct inferences about the preferences of others. And after that, the agent should also be available to explore possible options and should be able to make ranking in order to find agreement. And the final thing is that it should be able to make, ideally should be able to plan for next moves. Given the current move that the agent took, it should also be able to plan ahead. And finally, because we use a non-zero sum game, it allows us to measure things such as the cooperation versus competition aspects between the different agents. So this is the first reason, is that we really need to evaluate these skills, and negotiation is a task that somehow encompasses many of these skills that are interesting for us to measure. The second reason is that it's also a very practical application, and AI models, even before LLMs, they have been used even for practical negotiation for example, chatbots. And this was even before LLMs. Now with LLMs, there are some also startups that they are trying to introduce LLMs in order to do contract preparation or contract negotiation and so on. So since these areas are now being introduced, the LLMs are now being introduced to these areas, now it's important to measure whether they could make good progress in negotiation or not. So that was the motivation first of why we need new evaluation methods, and why negotiation is important. Once we establish that, I would like to go over some details of the game setup that we have. So this is originally a negotiation exercise that was introduced to teach negotiation to people. And here in this work, we adapted in order to evaluate multi-agent LLMs. So the game consists of 6 parties, and these parties they have their different. They are different entities. They have their own goals, and they are negotiating the establishment of a new project. In this case, like a new airport or a new sport park or a new stadium, something like this. And these parties, they are negotiating over 6 issues, and the issues are linked to the priorities and goals and preferences of each party. So, for example, the Green Alliance would want to reduce the environmental impact. The Workers' Union would like to increase its quota, and so on. So, the parties have each issue in the negotiation issues. It has different options under each. So for issue A, it might have option A1, A2, A3, A4. All of them, they also have semantic descriptions that are linked in general with common sense reasoning to the parties' goals. And the parties, they have secret scores over the issues, and they also have different priorities. And this is indicated by the pie chart here. So, for example, this agent would prioritize issue C over the others, and then issue B, and they don't care about the rest. And also, in addition to that, they have some secret thresholds. This means that this agent will only accept a deal if it satisfied its own secret threshold. So agents start communicating with each other over rounds, and usually they start from their ideal deal. And then during negotiation, during interaction, they should ideally make compromises over their ideal deal in order to reach a common agreement. So this is a graph that we have over one of the experiments that we had with GPT-4. So I would like to spend a minute in order to talk about this graph, because I use it consistently all over the paper and also all over the rest of the talk. So in here, this is the leading agent. So I might have forgot to mention that, but the parties, they have a leading agent, and it's responsible for coordinating, and also it makes the final deal towards the end. So the leading agent starts from its ideal deal. So this deal gives itself 100 utility. But then over rounds, it starts compromising, and this would decrease the score that it proposes for itself. So this is the deal that this agent, pink agent or the leading, is proposing over rounds over the negotiation history. And this is the dashed line, the horizontal dashed line, it's minimum threshold. So looking at this graph here, it seems like that the agent doesn't really go under its minimum threshold, which is a good sign. And on the other hand, here, the black line is the average utility of the whole group. And this is secret to the agent. So the agent is making compromises, but it doesn't really see, and it's not really given the information of how these compromises are affecting the group. But the increased utility, it means also a good sign that agents are more likely to reach agreement. And in general, all over the slides, if the dashed line is pink, then this means that this agent is the pink agent, is the one that's making the deals over thresholds, and so on. So the scores and the thresholds, they control the set of feasible solutions. And that's a good thing, because it gives us a way to reliably quantify the success and quantify the performance of different agents and different models. And I will talk later about how controlling the set of feasible solutions can also give us a way in order to increase or decrease the difficulty of games. So given the setup, we then next provide a baseline in which agents they can use in order to interact and play the game. So our baseline is based on a structured chain of thought that aims to decompose the task into smaller ones. So at each round, we select one agent randomly, and this agent is given the history of the public interaction. It's also given an initial prompt to describe the game and describe its own score, and it's given its previous plan. And we have something called incentive. So this means that the baseline is that we tell the agent that you are willing to compromise as long as your minimum score is met and you want to reach an agreement with everyone. And we later change this. And then the structure prompt is that we decompose the task. So for example, we tell the agent, we prompt it to look at the previous history and try to make any conclusions about the preferences of parties. And the next thing is the exploration. So we tell the agents that given the preferences of given the previous history, can you find deals that likely to lead to success? So in here, we can find that the agent can adapt to the history automatically or autonomously. So for example, it first proposed a deal, and then it later said that this party has a veto power, which we give that in the history of in the game rules. I forgot to mention that, but there are two parties, they have veto power, and this means that any deal has to satisfy the preferences of these two parties. So here, the agent automatically would adjust its own deal in order to make it more likely that the veto party would agree, and to make more compromises toward that. And the last step is that we instruct the agent to plan ahead and to consider what possible next actions it could take in order to in the next step. So I would like to briefly talk about the main results that we had. So we propose this as a benchmark where we can evaluate different models and different interactions between models. So given the metrics that we defined, which is like the success 5-way means that at least 5 parties are agreeing, meaning that their thresholds were met, and this must include the veto parties. And the 6-way means that all 6 parties are agreeing. And the wrong deals means that these are the percentage of deals that agents made, but they are less than the thresholds of the agent. And if we have a higher percentage of wrong deals, means that we have more failure in calculations. So the lower, the better. And we can see this in here that GPT-4 is leading in this according to these metrics. But we also see that some of the open source models, they are better than GPT 3.5. And also one interesting thing is that we found that smaller models like Llama 2 7B, also Mistral 7B, they failed at all to follow the instructions of the game. So we didn't proceed with them. So the other thing is that we evaluated is why do we have multi-agent setup to begin with at all? Because there are some now, a couple of months later after this work is done, there are some benchmarks on a negotiation evaluating it with LLMs, but they are mostly about 2 agent games or 2 players. So we explored whether it's meaningful and it's helpful to increase the number of agents. And what we found is that if you add more agents, so in here in each of these experiments, we vary the number of players. We keep everything fixed, but we don't instantiate some players, we drop them. And we found that when we add more players, we decrease the possibility that the deal would lead to all-way agreement. So also something I forgot to mention is that for each of these experiments, we repeat the experiment with like 20, 30 times or something with different runs, and we compute the percentage of success and all the metrics over the different runs. So what we found here is that when you add more agent, it's less likely that you will end up with all-way agreements. And it means that we have more difficult game, which is something good to have because it means that the benchmark is not so easy to solve. And so far, we assume that we have all agents are instantiated with the same model. So previous experiments where all agents were GPT-4, all agents were Mistral, and so on. But in practice, if we used multi-agent LLMs, it might be possible that some parties would have different LLMs. So we evaluated a mixed population of like some parties would be GPT-4, the others would be GPT 3.5, or in a sense, some parties might have stronger models than others. And since it's a cooperative game, so it's not a zero-sum game. It's not like we have one player that's supposed to win. So it's kind of really you have to find a solution for the group. So what we found is that if you introduce weaker models, you can have lower payoff for the group or lower success rate for the group. And this is especially the case if the leading party, which is P1, if the leading party is a weaker model, we can find that, well, first of all, if it's really making deals that's less than its own threshold, then this by definition means that it's not successful for the group because these are the rules of the game. It also, of course, means that the agent is failing in calculation, but it also means like failure in reaching agreement for the whole group. And something else what we found is that if we have weaker agents, they might end up with a lower payoff compared to the case that if we ran the same simulation but with all parties GPT-4. So in here, in the first plot here, we have this is the leading party P1 deals that is making over rounds. And this is the corresponding value of its own deal with respect to some agent. So this agent in this case is GPT-4. And this is the same game, but P1 is GPT-4, but the other agent is GPT 3.5. And what we found here is that the P1 would give deals that overall would give lower scores and lower values for the other GPT 3.5 agent. So in conclusion, what I wanted to say from this is that we might have fairness considerations. So if you start the game with an unbalanced setup where you have weaker agents, you can end up with a case where these agents would get a lower payoff by the moderator or by the leading agent just because you started the game with these weaker models. So I would like to move to the last part of my presentation. So far we assumed a cooperative scenario. So which is the incentive that I talked about briefly, is that you prompt the model and you prompt the agent specifically to be cooperative. You tell it that you prefer to have any deal over no deal at all, and you want to have a deal that's the only criteria that you need to maximize is that you need to satisfy your own threshold, and then that's it. But this is really a dreamy scenario. We might not have this in practice. In practice, you can end up with greedy agents or adversarial agents where one agent is aiming to maximize its own score over the whole group. So this is what we do next, is to see what kind of safety consideration we need to pay attention to if we have this multi-agent scenario. So we have two scenarios here. The first one is that we prompt agents to be greedy. We prompt them to maximize their own score as much as possible. And the second scenario is that we prompt agents to sabotage the negotiation. We tell them that you will have a higher payoff if you sabotage the deal. And we, similar, inspired by ML attacks, we have a targeted and untargeted version of this adversarial agent. So the targeted, we would prompt the agent is that you really need to attack this particular victim. The untargeted is just to tell it that we want to sabotage the negotiation. It doesn't give it a target to go after or something. So for the attacks, we mainly ask two questions. Is that the first one, we don't give, in all of our simulations, we don't give agents any instructions on which deals they should propose. There are over 700 combinations of deals, and you just tell it its scores or its objectives or its incentive, and we hope that this would be translated to something meaningful. So the first question is that, can we modulate the agent's actions only with high-level incentives, like being cooperative or greedy and so on, without giving specific instructions? And what we found is that it's really the case. So in the compromising game, this is the same agent, but it's instantiated with different incentives, different simulation runs. So in the compromising game, you can find that the own score of the agent, so this is what the agent is proposing for itself, it's relatively lower, but the collective score for the group is higher. In the greedy game, the agent is still interested in finding compromise, but it's also aiming to maximize its own score. So the own score of the agent is high. And in the adversarial game, the own score is also high, but the collective score for the group is relatively lower than the compromising and even the greedy. And the targeted game, again, this is the perspective of the adversarial agent, and this is the deals that it's making and its values with respect to the target agent. So what we found here is that the adversarial agent in this simulation, it found deals that maximize its own score. It also reduced the collective score for the whole group. But compared to C, or the untargeted game, it also specifically targeted the target agent, which is something that was not really the case in previous simulations. And again, it was never given as exact instructions of what deals to propose in each of these simulations. And it turned out it's something that's not really trivial to have when we tested out weaker models, like when we tested out 3.5. So we have here this very neat and clear separations of what everything it should be, and it's following the same kind of logical scenario that we imagined. But in GPT 3.5, it's all over the place. So we don't have any distinction. Everything is basically the same thing. So it shouldn't be the case. And so it turns out that the translating the incentive to actual specific actions is not really very straightforward to do. So that was the first question. And this last thing that I'll talk about is that how can these actions really affect the group? So it could be that the agent is doing all these correct inferences and all these correct deals that it should do, but are these actions affecting the group in any way at all? So what we found is that it actually affects the group. So for example, here, this is the fully cooperative setup. We have a higher success rate, but if you introduce a greedy agent, you can have a lower success rate. If you introduce two greedy agents, again, you have a lower success rate. And especially if the target agent is greedy, you can have the lowest, because again, remember that it's a cooperative game. And also, when you have sabotaging variance or you have adversary variance, even the targeted or untargeted one, we again can have lower success. And again, we also track the deals of the leading agent over rounds, and we see that, for example, here, if we compare the cooperative and the greedy variance, so we can find that in the greedy game, the leading agent gave deals that sort of give preferences to the greedy score. So the greedy greedy agent. So the greedy agent managed to somehow get higher scores for itself, given by the leading agent P1. It's also the case for the targeted agent or the in the adversary game. So when we compare the two figures in the cooperative game and the targeted game, we also can see that the target score is lower. These are the scores made by P1. So P1 gave disadvantage, sort of like it didn't favor the target score, and in a sense, the adversarial agent succeeded in sort of convincing convincing. I'm just using a very humanizing word, so of course it's not convincing, but it's kind of like getting the leading agent to give less preferable deals to the target. And also, we observe interesting sort of qualitative results is that in lots of cases, the adversary could manage to create a group effect against the target agent. So here, the leading agent in one of the interaction runs, it could say that the benefits of the deal to myself and to the Green Alliance, which in this case was the adversary agent, they outweigh the disadvantage to the target and to the other affected parties. One thing that we found is that sometimes it's a good sign is that sometimes the other agents identify the adversary. So again, in all of these runs, none of the agents were given the information that there is an greedy or that there is an adversarial agent. But in this case, one of them identified that, well, the preferences of this party is very different from the group and very significantly different from the other parties. And this could mean that potentially we could have some defenses against these attacks by having a moderator or by having some sort of adaptive defenses where you prompt each of the agent that you might have an intruder. So try to take that in consideration when you make deals, something like this. So one final aspect is that I talked before about memorization of benchmarks. And one good thing, in my opinion, is that you can easily adjust the difficulty of the game. So remember that I mentioned that you have minimum thresholds and you have scores, and you can adjust the scores and minimum thresholds in order to increase or decrease the set of feasible solutions. And this means that there is no fixed solution for the game. It's not like, oh, these are the set of deals that models could memorize if this benchmark got leaked somehow in the training of models. You can change this. This is a hyperparameter that you can do, and you can end up with very different instantiations of different games. And you can find here that if we really decrease the set of feasible solution, we can also decrease the success overall. And also, it's possible to create new games altogether. So we use GPT-4 to write different games. So we don't give it the previous game, but we just tell it the criteria that we want to have in the game. And we ended up with a lot of diversity in the description of the games, in the rules and the scores and so on. And again, these are all different ways where we can adjust the benchmark in order to have evolving and easily adaptable benchmark to test future models. Hopefully, the goal is to have more sustainable benchmark. So that concludes this part, concludes my talk overall. Yeah, I'm happy to take any questions, but what I wanted to really say is that I believe that multi-agent negotiation, multi-agent games in general, can be really a great tool to measure dynamic interaction, to have dynamic benchmarks between agents. And they're also very great to measure many of the subtasks like arithmetic, planning skills, and so on. And they are easy to control, so hopefully they could be sustainable. And also, it's very important to measure complex coordination and complex interaction between agents, which is something that we didn't have before in a single agent setup or even in a static setup without interaction. So yeah, thank you so much. And I hope to answer your questions if you have any.
Okay, sir, thanks for your great talk. It was very interesting. So yeah, are there any questions?
Maybe I can ask a question. So if I got it right, you generated the game via LLMs, right?
The first one is not generated by LLM. So the first one is it was a game that was already used for, like, the base game that we use for most of our experiments is that it's a game written for humans, and we took it and we wrote our own description of the game. So we've verbalized it in a different way in order, again, to avoid any kind of memorization thing. We also did some adjustment where we changed the names of the entities and so on. But the other games that I've mentioned towards the end, they are generated by the LLM, yeah.
So then I have two questions. One is if you have information on how humans perform on this game, if LLMs will do better or humans do better, or maybe humans make more reasoning solutions, or they are more selfish in general, or something like that. And maybe this is a quick answer. And the second one was if you tried cross-model tests, so generate the game with one model or make tweaks to the game with one model and test it against another model, because I was wondering if they have different reasoning in generating and answering, and if they transfer across models.
That's a very cool point. So I guess the first question is that I'm not sure if there is a specific baseline to the game, and especially like and this is something that I would like to do next, maybe, or even introduce a human with the LLM, something like this, because it's not like a purely logical game, so it's not like we'll have a clear benchmark of like how humans perform, because the humans could be selfish, they could be cooperative, so it really depends. So I'm not sure the best way to do this, but I think it's interesting to sort of explore this. The second question is that, well, we didn't really do this, but I think that would be like to test the same game that was measured by GPT-4 across the other, because I think this could be interesting. It could give advantage to the model that generated the game. But also, as far as I know, there are some papers that said that, well, if you generate a problem with GPT-4, it's not really clear that the model would answer correctly what it generated. But yeah, I guess it would be definitely interesting to see if it would give advantage or give certain biases toward the generator model.
Yeah, thanks.
Thank you for the question.
So, are there other
Nice.
questions? Please raise the hand.
Yeah.
Okay, I see. There are questions. Paul, if you want, you can also speak up. Otherwise, we read it. Okay, I think we read it. Okay. So the question is, I guess a worst case scenario in a negotiation game would be that a party with a veto power would also be the adversary, right? Then what would be the outcome of the negotiation?
Yeah, that actually, I agree. So we did that. So this is one of the experiments that I mention in the slides, but we had it in in the paper. So in this case, you're totally right. Is that this would be the worst case scenario, but um, it's kind of like practical wise. I'm not sure what would be the scenario where the leading is also, or like the veto party is also, they want the negotiation to fail. I imagine the case where if the veto party is prompted by someone else, and in this case, like there is an intruder that took control of the veto party, but it could be that the veto party is masquerading and is trying to convince everyone that's playing fair and cooperating, but it's not really cooperating. It's trying to still give disadvantage to the group. But yeah, I agree. Thank you for the question. Yeah.
Okay. Maybe there is enough time for the question.
Let's see if anyone raises their hand. In the meanwhile, I have another question. So you mentioned that it could be possible to overfit to this benchmark as well. Would it be possible for a model to be stupid and overfit to this to this game? So, for instance, I create a model that only does this game, and for the rest is completely useless.
Yeah, actually, that's kind of funny, because in some is when I tried this with some of the models that were kind of stupid. So so for example, it could like if there are options A1, A2, and so on, so it could give like the middle in each of them, and in some cases the middle would give like a compromise for most of the parties. So it's the model is doing very bad in calculation, but it's giving the middle value. So that's why it's kind of like succeeding. And that's why I think it's important to change the games, because this might not be the case if you really change the score so much. So there are a set of feasible solution, or we did some also control things to swap the values. So it's not easy, like it's not kind of always straightforward that the middle would be the best solution, sort of. So I think it could be the case that you can the model could hack the evaluation, but it's harder to hack this if you do the interventions, that you change the scores, you do different variations. So I think it's less likely to overfit to this.
All right.
Or I believe so. Hopefully.
Well, I was curious because, you know, the first thing that comes to mind is, okay, let's make the model learn the rules of the game perfectly and the game perfectly, but maybe the model forgets the rest of the word. And that's probably the case
Yeah.
if you try to.
Yeah.
All right. So I think there are no other questions. So thanks again, Sahar, for bringing your expertise in LLMs to our seminar. That was a great talk.
Thank you so much.
And thanks
you so
everyone for
much.
joining today. Oh, sorry. Thanks everyone for joining today, and see you at the next seminar. Bye-bye.
Bye, thank you. Bye.
Okay.
Okay, we stopped the streaming.